A variant enzyme created by engineers and scientists at the University of Texas at Austin can break down in hours or days plastic waste that nature takes centuries to degrade. This discovery, published in Nature, could help solve one of the world's most pressing environmental problems: what to do with the billions of tons of plastic waste that accumulate in landfills and pollute our land and natural waters. The enzyme has the potential to power large-scale recycling, which would allow major industries to reduce their environmental impact by recovering and reusing plastics at the molecular level. The possibilities are endless across industries to take advantage of this cutting-edge recycling process, Hal Alper, professor in the Makeda Department of Chemical Engineering at UT Austin, said in a statement. Beyond the obvious waste management industry, this also gives corporations in all sectors the opportunity to take the lead in recycling their products. Through these more sustainable enzymatic approaches, we can begin to envision a true circular economy of plastics. The possibilities are endless across all industries to take advantage of this cutting-edge recycling process. The possibilities are endless across industries to take advantage of this cutting-edge recycling process. The project focuses on polyethylene terephthalate, PET, a major polymer found in most consumer packaging, including cookie packaging, soft drink bottles, fruit and salad containers, and certain fibers and textiles. It makes up 12% of all global waste. The enzyme was able to complete a circular process of breaking down the plastic into smaller parts, depolymerization, and then chemically rejoining it, repolymerization. In some cases, these plastics can be completely broken down into monomers in as little as 24 hours. Researchers from Cockrell's School of Engineering and College of Natural Sciences used a machine learning model to generate novel mutations in a naturally occurring enzyme called PETase that allows bacteria to degrade PET plastics. The model predicts which mutations in these enzymes would achieve the goal of rapidly depolymerizing post-consumer waste plastic at low temperatures. Through this process, which involved studying 51 different post-consumer plastic containers, 5 different polyester fibers and fabrics, and water bottles made of PET, the researchers demonstrated the effectiveness of the enzyme, which they call fast PETase, functional, active, stable, tolerant PETase. This work really demonstrates the power of bringing together different disciplines, from synthetic biology to chemical engineering to artificial intelligence, said Andrew Ellington, a professor at the Center for Systems and Synthetic Biology, whose team led the development of the machine learning model. Recycling is the most obvious way to reduce plastic waste. But globally, less than 10% of all plastic has been recycled. The most common method of disposing of plastic, besides dumping it in a landfill, is to burn it, which is costly, energy-intensive, and spews noxious gases into the air. Alternative industrial processes include the very energy-intensive processes of glycolysis, pyrolysis, and or methanolysis. Biological solutions consume much less energy. Research on enzymes for plastic recycling has advanced over the past 15 years. However, until now, no one had been able to figure out how to make enzymes that could operate efficiently at low temperatures to be portable and affordable on a large industrial scale. Fast PETase can perform the process at less than 50 degrees Celsius. Next, the team plans to work on scaling up enzyme production in preparation for industrial and environmental application. The researchers have filed a patent application for the technology and are considering several different uses. Landfill cleanup and greening of waste-intensive industries are the most obvious. But another key potential use is environmental remediation. The team is looking at several ways to get the enzymes into the field to clean up contaminated sites. When considering environmental cleanup applications, you need an enzyme that can function in the environment at room temperature. This requirement is where our technology has a big advantage in the future, Alper said.